All right, now that we have kind of discussed acids and bases, the second part of this lecture is going to be about how acids and bases interact in solution, how we can determine the reaction of the acid or base with water, and also how to calculate pH using the acid dissociation constant and pH using the base dissociation constant. But a couple of things first that we need to kind of review or revisit. The generic format for an acid's reaction with water is HA plus water gives us hydronium ion plus the conjugate. Remember, everything is aqueous except for water, which is considered a liquid. Because an acid, by definition, is a proton donor, therefore, the acid gives up a proton, and that giving up of a proton goes to water, creating H3O plus. This is the generic format where A is an acid. Let me give you an example of what this looks like in an actual compound. So you can also look at, let's look at nitric acid plus water, liquid, gives us again, remember, we label each of these a certain way. We label the acid and the base with the conjugate and the conjugate base. Remember, nitric acid is the acid in this case, water is the base, hydronium is the conjugate acid, and nitrate is the conjugate base. Remember from our list that nitric is a strong acid, so we expect complete dissociation here. So this is the interaction of an acid with water, okay? Now, if we want to take a look at the interaction of a base with water, then we generically write this as base plus water gives us the base with a proton now and hydroxide. Here's a scenario where water is the acid and donates the proton to the base, which is the acceptor, and it wants the proton, it wants the H. So in this case, an example of this would be ammonia plus water gives us ammonium plus hydroxide. And there is an example of an actual example of a base plus water. Now, what's happening in each of these? You just need to stay consistent when we're talking about acids and bases. If it's an acid, the H goes with water, creates hydronium every single time, if it is in fact an acid. If it's a base, then water gives up a proton every single time. If we need to label these as conjugates, we label the ammonium as the base, we label water as the acid. We now have a conjugate acid as ammonium and a conjugate base. Okay, so generically speaking, the formation of hydronium ion leads us to an acidic solution, and that means that we have a pH that is less than 7. Anytime a hydronium is created, notice we have no hydronium in this example. Hydronium created, acidic pH. When hydroxide is created, we end up with a basic solution. We end up with a pH greater than 7. So if you get a generic question like, hey, what should the pH be if this is added to water? Hydronium is formed or ammonium is formed. And remember, in these examples, all of this is 1 to 1 to 1, but you also need to balance these if necessary. All right. Let's talk about a strong acid, particularly HCl. Let's look at HCl. So if we had HCl added to water, We expect what to happen. HCl is hydrochloric acid. It's an acid. We expect it to give up its proton. We expect it to then form hydronium because water in solution wants to pick up that proton. So we end up with hydronium, which is what we expect, and we end up with chloride ion. When a strong acid and base is involved, we are talking about complete dissociation. So, if this completely dissociates, then when we look at the equilibrium expression, remember that water does not involve itself in the equilibrium expression. When we see this equilibrium expression, the fact that we show complete dissociation means that this value here is approaching zero. It is pretty much almost zero completely. What does that mean? That means that KEQ is very, 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 very big. So we're looking at it being much, much larger than 1. But if we assume complete dissociation, which is what we assume in this case, then KEQ is greater than 1. We actually don't ever worry about or study the equilibrium constant for strong acids, because as this approaches 0, we start to deal in some non-real numbers. Remember, we can't really divide by 0. But when we're dealing with strong acids or strong bases for that matter, the equilibrium expression, this pretty much goes to 0. So what do we do with that information? We use this to determine the pH if we added HCl. And because of that, if complete dissociation occurs, then therefore the concentration of HCl has to be equal to the concentration of hydronium ion. These two are going to be equal. And the reason that they're going to be equal is because of complete dissociation. This is not going to always be the case. We're going to see here in a second that this is not always the case. But in this particular instance, this is equal to this. Therefore, pH is equal to negative log of the concentration of the strong acid, if these two are equal. So, for example, if I told you that you had 0.05 molar HCl, then to get the pH of that, we would take pH equals negative log 0.05 molar. And that would give us the value for pH once we plug this in the calculator. Again, it is not minus sign, it is negative log of the concentration. And this is the same for a strong base. And let's show that example. So given a strong base such as sodium hydroxide, which is what we were working with in the laboratory, we notice that if the sodium hydroxide interacts with the water is going to act as the acid and donate the proton. Since water donates the proton, then we're looking at creating more sodium hydroxide. And this sodium hydroxide, if we broke this down, we know it completely dissociates. So we know we actually are getting this as our product. That's what we're getting as our product. We're actually getting hydroxide. And the formation of hydroxide, in this case, is going to give us exactly what we were looking for. So when we're talking about KB here, again, KEQ, when we're talking about the equilibrium expression, if we have complete dissociation, then the concentration of the base is equal to the concentration of hydroxide in solution. And therefore our pOH is equal to negative log of our NaOH. And this example is just like the previous one. So in this instance, we do have the exact same concentration for our starting and what we expect to be in solution. And again, this is for strong and strong. There are only 6 strong acids. We've already talked about those. And there are numerous what we call weak acids. Numerous weak acids. And by definition, a weak acid does not dissociate completely. A weak acid does not dissociate completely. So what we expect from a weak acid is that some of it releases protons and some of it doesn't. So looking at a quick example, let's take a look at acetic acid. HC2H3O2, we work with that in the laboratory. This is vinegar. Acetic acid ends up allowing us to donate this proton. Again, the acidic proton is here. That acidic proton is donated to some degree to the water, just like before. There's nothing different in the reaction. The only thing different here is that we are not completely dissociated. Therefore, our KEQ is not exactly my starting concentration. So now when we take a look at KEQ for this particular reaction, we see hydronium, we see the acetate, and then we see our starting acid. Again, remember, this is the acid, this is the base, this is the conjugate acid, this is the conjugate base, and KEQ is always products over reactants, always. Now, the gear that we have to switch in our case now is that yes, this is an equilibrium expression, yes, KEQ works fine, but when we're dealing with acids, you will see that we now call this Ka, K sub A, big K, little a. And this is known as the acid dissociation constant. Now, the acid dissociation constant is going to be given to you in scenarios where you need it. It is in your reference material. It says tables of Ka and Kb. Tables of Ka and Kb. You want to look that up in your reference material, go ahead and print you out a copy, and I have that with you for all of the work from here on out in acids and bases. So this is Ka. The size of Ka, right, the numerical value of Ka tells us how much this weak acid dissociates, because the numerator here is a function of how much. Acetic acid has a Ka of 1.7 times 10 to the negative 3. So the Ka here, 1.7 times 10 to the negative 3. This is a very small amount, right? This Ka is less than 1. Less than 1. Therefore, that means we should remember from our Le Chatelier's principle and our equilibrium discussion, if this Ka is less than 1, then reactants are favored. So the majority of vinegar is actually still in this form. It does not create the acid, only a small amount, shown by this Ka value here. So again, how to set up the Ka expression for an acid in water is shown here. Products over reactants, and you want to write this using Ka denotation. All right, let's talk about bases. Okay, in this case, we're going to use methylamine as the base. And now we're going to say that a weak base does not associate completely. And the reason I'm changing the words here, associate, is because a base, remember, accepts protons. A base accepts protons. Remember, if it is a base, then it is going to accept the proton from water in solution. It's going to create the conjugate acid and form hydroxide. We know the pH in this particular case is going to be greater than 7. We want a greater than 7 pH. Okay, we have a reaction 1 to 1 to 1. We're balanced. Everything is good. We have our phases, but we do not have complete association. Now, if we looked at KEQ, we see that KEQ is concentration of the conjugate acid, concentration of hydroxide over concentration of the base. When dealing with bases, we have an expression KEQ, and we call this KB. Just like it's KA, we have KB. And KB tells us how much this associates with protons from water. If it was a strong base, it would take all and associate completely. Since it's not a strong base, it is a weak base, it's only going to take a certain amount of these protons from water, creating only a certain amount of hydroxide. So the KB for methylamine, 4.4 times 10 to the negative 4. An even smaller value, much less than 1. We know that means that reactants are favored, which means that only a certain amount of this associates, creating hydroxide and shifting the pH. So a weak base and a weak acid do not completely dissociate or associate with water. It only reacts to a certain degree. And that's what KB tells us. And KB is now extremely important to determine the pH of a solution, or to determine how much, or to the pH can be used to determine the Ka or Kb. So we're going to show how that can be done in both instances. How do we apply this knowledge now, and why do we care? So the next thing we're going to do is we're going to determine the pH of a weak acid solution from the Ka. So let's take this acetic acid, and let's say that we have a concentration of acetic acid that is equal to 0.03 mole. And we know the concentration. Since we know the concentration, we need to now take a look at how this is in equilibrium with water, and we know that from our previous knowledge. We need to set up the reaction. Now that we've set up the reaction, just like any other equilibrium problem, we have assumption that this is our starting concentration. We assume that none of the dissociation has necessarily occurred yet. If we could go to the point, the immediate point where we dissolved the acetic acid in the water and take that as the initial, if we wrote the ice table and we show that this is 0.03, remember we do not care about liquids, because pure liquids do not find themselves in the equilibrium expression. Here, we're starting with 0. The change is minus x. The change here is plus x, and then we end up with 0.03 minus x, and x. Very important to understand this concept. Just because we are doing acids and bases, it doesn't change our rules on setting up equilibrium and using the ice table. So we have a concentration, we now have our equilibrium amounts, and we can use that to write our equilibrium expression. And our equilibrium expression for this particular case is going to be Ka is equal to x times x over 0.03 minus x. And we should know how to solve this here. Now, a little shortcut that I'm going to now introduce to you, and that you can utilize this, is we've always learned to drop this. We've always learned to use this x and set up a quadratic equation. But now that we're dealing with acids and bases, there is a shortcut that we can use to determine if you can drop the x. So the shortcut is, if the concentration of the acid over the Ka is greater than 500, the minus x can be dropped. It's very important. So I'm going to show you the example. First, I need to write for you the Ka for acetic acid. Again, this is a constant. It will be given to you in reference materials. It's 1.7 times 10 to the negative 3. If we do our test, and say 0.03 divided by 1.7 times 10 to the negative 3, and we put this in the calculator, we can confirm what this ratio is. And this ratio is 17.6. Okay? That means that we cannot drop x in this case. It is not large enough for us to drop x. Therefore, we need to keep x. Now, let's say that we were dealing with a concentration of 0.5. Actually, let's go a little bit further just to get that. Let's say we're dealing with a concentration of 1.5. Dealing with a concentration of 1.5, we get 800, right? If we had a concentration of 1.5 or about 1 or higher, then we can drop x. But in this case, we cannot drop x. So we would need to then solve this for x, and the solution for x here will give us